My name is Steve Skiena. I'm a professor at Stony Brook University and the director of the AI Institute at Stony Brook. And I have a long-term research interest in graphs and applications. Many people know me as the author of a couple of books, the Algorithm Design Manual, which basically goes and tries to show where graphs are used, graph algorithms and graphs are used for modeling and things like that in computer science. And more recently, a book on data science, the Data Science Design Manual, where we start to look at how do we make sense of large amounts of data, some of which is related to graphs and certainly seems to be in the wheelhouse of what people are doing here. So my research these days is focusing a lot on graph embeddings. Graph embeddings are kind of representations, moderate number of dimensional representations of graphs where vertices are represented as points in space. Ideally, you would like to take a graph and reduce it to features that you could build in a machine learning model. And machine learning models typically work very well with numerical values, things like linear regression, things like SVMs, things like neural networks, work very well with data when it is kind of in a numerical representation. And our goal is to take a graph and represent it in, let's say, 100-dimensional space, so that these 100 dimensions represent features. They're not so much about visualizing graphs. You're not going to look at a picture in 100 dimensions and make sense. But on the other hand, a machine learning model can very easily take sense of 100 features. And by reducing graphs to these features, you can, easily build interesting models and powerful models. You can easily answer questions like, when are two things very similar to each other? Testing whether 2 points in a high-dimensional space are similar, or finding what the most similar things are perfectly reasonable things to do once you have a representation. And our graph embedding algorithm, DeepWalk, is a way of getting these kind of embeddings. It's based on, a lot of its power comes from this idea of word embeddings. Many people have heard of word-to-vec. This is a way of taking English text in an unsupervised way and reducing it to features that would represent what words mean. You would like it to be the case that words that have similar roles in language, like green and yellow and red, all do similar things in language. You would like to find a way to kind of organize the words so that these words are close to each other in space because they do similar things, and this is very powerful for building language models. So DeepWalk takes this idea of building representations of essentially words, by their corresponding role of things like that they fit in sentences. That's what word-to-vec does. By an analogy, we think about a graph as being a vocabulary of vertices, And we think of sentences as being walks on a graph. A walk from one word to another word to another word, that describes a sentence. And a walk from one node to another node to another node describes a random walk, which we can now treat as a sentence for the purpose of building embeddings. So we use basically the underlying technology of word-to-vec, take sequences of symbols, and from them in an unsupervised way, learn what the symbols really mean. We do a similar thing for graphs. And this has been proven powerful in a lot of applications and apparently is on its way into the library at Neo4j. So graph algorithms are a very interesting area of algorithm design. One thing is that a lot of graph algorithms are very, very intricate, but using them does not really require knowledge of their intricacy. A lot of the power in graph algorithms comes from basically knowing how to model what you're doing. And so that you can actually build surprisingly powerful things out of graphs from relatively, without knowing that much about the underlying algorithmics or how it works. And the fact that graphs are ubiquitous in social networks and networks anywhere means that it is very, very powerful things. Graphs are a fundamental part of computer science. They will always be a fundamental part of computer science. But obviously, graphs have been getting bigger. The amount of graph data and the amount of graph representations has been growing tremendously. Obviously, we know about social networks. We know about graphs seemingly are everywhere. And it's clear that that trend is presumably only increasing. You know, with our graph embedding system, DeepWalk, we originally built it to handle a few million nodes, and that sounded very exciting, except graphs keep getting bigger and bigger. And so our more recent research is focused on hierarchical graph embedding, something we call HARP, that it will enable you to build bigger and embeddings for bigger graphs using distributed algorithms and things like that. It's very, very interesting for an academic, especially one who has spent his life teaching graph algorithms, to see so many people interested in graphs. It's been kind of interesting coming to this Neo4j event. And I'll admit I've been surprised by the number of people and the amount of activity that goes on in this space. And again, graphs have become very powerful, they're very fundamental, and they're only becoming more and more important.